Hello all, I'm Professor Archana Buruzwale, working as assistant professor in computer engineering department. In this video, we are going to discuss the memory placement strategies. Let's go through it. So, memory placement strategies. There are four algorithms are there for searching the list of free holes. As we know, the contiguous memory allocation, there are two types of allocation, the contiguous allocation and the non-contiguous allocation. So memory placement strategies comes under the category of the contiguous memory allocation under the variable partitioning method or dynamic partitioning method. So under the variable partitioning method or dynamic partitioning method, there are the four algorithms are there for searching the list of free holes. That free hole can also be called as a hole. That free block can also be called as a hole or can also be called as a free block or a hole for a specific amount of memory. So those strategies or algorithms are first fit, best fit, worst fit, and next fit. So these four algorithms are there. There are the different ways in which they search for the free hole for a specific amount of memory. So let's go through all these techniques one by one. So first of all, the first fit technique, what it does, it allocates the first free block. It allocates the first free block or first free hole that is large enough for the new process. This is a fast algorithm. It starts from the initial first free hole which is available in the memory. It starts searching from that, and wherever it finds a match with the process size, if the process size is zyada, if it is larger than the process size, then in that case it allocates it immediately. Whichever the block it finds first, that will be get allocated to the particular process. We'll just see the result technique through the illustration. So you can see here, this is the initial memory mapping. You can see, so OS is resident in one part of the memory. After the OS, three processes are there which are already there in the main memory. This is the initial memory mapping. P1, P2, and P3. These are the three processes which are there in the memory, and three free holes are there, one of 10 kb, another of 16 kb, and third one of 4 kb. These three free holes are there. They are also called as the free blocks or holes. Okay, so this is the initial memory mapping. Now with the first bit, if new process arrives of some x size, so where it allocates that memory, we'll see that. Suppose the P4, that is the next process, P4 of 3 kb arrives. So what it does, it has to allocate the memory to this particular process. It has to allocate the memory to this particular process using first fit algorithm. So first fit algorithm is what? It allocates the first available hole which is large enough to occupy this particular process. So it starts searching from this particular free hole, right? Because this is the first hole. So it starts searching from here. The first hole itself is of the 10 kb, which is larger than the process size 3 kb. So yes, it is large enough to occupy this particular process, right? It will not search for the exact size. What it will search? It will search for the first hole which is large enough for occupying this particular process. So my condition is satisfying over here. So what it does? It occupy the process P4 in the first free hole of 10 kb. So P4 is occupied here of 3 kb, and there is a this particular 10 kb free hole gets internally fragmented between the process size of 3 kb and the free memory of 7 kb. So this 7 kb is free, but it is internal to this partition. It is internal to this partition. So this is called as a internal fragmentation. Okay, we'll see one more. Suppose one more process comes for this under this technique. So how it occupies into the memory, or how it gets loaded into the memory. So suppose the next process arrives, P5 of 15 kb. P5 of 15 kb arrives, suppose here. So it will start again searching from the first available hole. So first available hole, this is available, but it is internal to the partition, so we cannot use it. So it will skip, it will start searching from here. So here it will find that it is this free hole, it is of size 16 kb. Yes, this free hole is larger than what the process size is. Yes, so we can occupy the process over here into this free block. So the process P5 gets loaded over here into this free block. So this internal, whatever the free block of 16 kb is there, so it gets divided into the two partitions, process size 15 kb and one free internal fragmentation of the 1 kb to that particular partition. So this is how the first fit works. Okay. So we'll move on to the next technique, that is the next fit. This is another memory placement strategy. The next fit is basically the modified version of the first fit. It begins as the first fit only to find a free partition when the particular algorithm is called first time. When the algorithm is called first time, it acts same as the first fit only, but from the next time, it starts searching from where it left off, not from the beginning. It starts searching from where it left from, not from the beginning. Okay, so that's why it is called as the next fit. This policy makes use of the roving pointer. The pointer moves along the memory chain to search for the next available hole, which is fit for the memory and the particular process size. So this helps him to avoid the usage of memory always from the head of the beginning of the free blockchain. So no need to search the entire list again and again. That what we are doing in the first fit. In the first bit, every time whenever the new process arrives, you have to start from the first free hole, start searching from the first free hole unless and until you find something whole uh, which is big enough, large enough for the particular process, and then you will stop. But here in the next fit, you will not always start from the first fit. We will not always start from the first hole. Only first time you will start from the first hole, and from the next time onwards you will start from the second second particular available hole, or the next available hole from where it left off in the previous iteration. Okay, so you can see here the initial memory mapping for the particular next bit, same as the first bit. You can see here the same mapping I have taken here. Suppose the new process P4 arrives of 3 KB. So initially first bit, next bit works as the first bit in the first iteration of the program. Okay, so initially it will find the first free available hole. So first free available hole is a 10 KB, which is larger enough than this 3 KB. So it will occupy the process P4 over here using the next week. Okay, so now here after this, whenever some new process comes, it will not start searching from this particular available hole. It is where the particular process left off in the first iteration. So it will start searching from the next available hole in the next iteration. So it will start from this particular hole in the next iteration. Okay, so here you can see that suppose new process arrives, so it will start searching from here and it will occupy that process here, because it is the hole which is of 16 kb. It is large enough that for this particular process to occupy, that is of 15 kb. So we can occupy the load the process over here. So this is how the next fit works. Very simple, same as the next first fit only. Only the difference is from the next iteration it starts searching from where it left off. That's the only difference between the first fit and next fit. Now we'll go for the third placement strategy, that is the best fit. So best fit is the as the name itself suggests that this is one of the efficient memory placement strategies. Why it is so, that also we'll see. Best fit. Suppose here it allocates the smallest block. It allocates the smallest block among those that are large enough for the new process. Means it will not do like that. Whatever the available hole is there, it will allocate to that particular process. It is not like that. What it does, it searches through the entire list of the available free holes. It searches through list of available free holes, and from those free holes, whichever the block is just large enough for the particular process size. Means suppose the process size of 3 kb, and suppose among the list of free holes, one of the hole is of 4 kb, then it is just enough for the particular process, and all the other holes are more than 4 kb. So in this case, best fit, it will select the hole of the 4 kb which is just large enough for occupying the process of 3 kb. So smallest possible hole it selects. So in this method, the OS has to search the entire list, or it can keep it sorted. Either we need to every time search the entire list, or we can keep the list sorted. So either of these two we need to work or implement, and stop when it hits an entry. And when the particular algorithm stops, when it hits a particular entry which has a size larger than the size of new process. So this algorithm produces the smallest leftover block. However, it requires more time for searching. Obviously, it searches through the entire list, so obviously it will take the more time for searching all the list or sorting it. Either you are searching it every time, or either you need to keep the list sorted and just get the particular hole for that. So in both cases, you require the more time. So if sorting is used here, then merging the area release. When we merge the area release, suppose one of the process has finished its working, so it will release the memory region. Suppose the process size of the 5 KB. So it will release the memory region. And if the whole which is of the 5 KB is released and uh, the neighboring whole of that 5 KB is also free, so we need to merge those areas to have the contiguous block of the memory. So in that case, merging the area released when the process terminates to neighboring free blocks becomes complicated because we are using the sorting. So in that case, we need to again run the sorting algorithm to keep the list sorted. So now we'll see the illustration of the base fit. So here it is initial memory mapping. You can see here, though as usual, the OS is there in the lower part of the memory resident, and three processes are already there, P1, P2, P3, and three free holes are there of 10 KB, 16 KB, and 4 KB. Okay, so this is the initial memory mapping. Suppose the next process arrives. The P4 of 3 KB arrives here. Okay, so now it is a best fit. So what it does, it searches through all the free holes. It searches through all the free holes which are available. Okay, so here it starts searching from the 10 KB. No, it is larger. 16 KB also it is larger. 4 KB. So this is the last hole available. So among these all the three holes, it finds that this is the exact matching to the process size. It is just large enough. Okay, so it will select the smallest available hole to occupy the process of size 3 KB. So it will allocate the process over here. So P4 gets loaded over here into this free block, and it is internally fragmented between, there is internal fragmentation to this block of 1 KB. Suppose the new process arrives here, P5. P5 of 15 KB arrives here. So again, it starts searching for the whole entire list of the free holes. So it will search, suppose here 10 KB, it will search, it is not large enough. Then 16 KB, it will search, yes. And then after that, there is no free holes available because this is the internally to this particular process P4. We cannot use it. So there are only two free holes are there, 10 KB and 16 KB. So out of these two holes, 16 KB is large enough for this particular process. So it will occupy the process over here into this hole. So you can see that the process P5 gets loaded here. And again, this partition free hole is again having the internal fragmentation of 1 KB. So this is the best fit. Now the last algorithm was fit. So what it does here, it allocate the largest block. It allocate the largest block among those that are large enough for the new process. So again, a search of the entire list of sorting is needed here. This algorithm produces the largest overblock. Means in best fit, what it does, it searches through the entire list and selects the block which is small and which is comparative to this process size. But here what it does, it searches through the entire list and select the largest block among all the list irrespective of the size of the process. So here it again search entirely. So here the algorithm produces the largest leftover block. So here it is the initial memory mapping. You can see that OS is resident in one part of the memory and three processes are there. P1, P2, P3 are already there and three free holes are there. Okay. Now we'll see how it works using the worst fit. So suppose the process P4 of 3 KB arrives. So what it does, it searches the entire list of the free holes. So it will start searching from here 10 KB, 16 KB, 4 KB. Out of these three free holes, which one is the largest? So 16 KB is the largest. So it will occupy this particular largest block or largest hole to the process irrespective of the process size. 3 KB is the process size which we can easily accommodate over here into the 4 KB block. But as it is a worst fit, name itself suggests that, so it works worst. So here it occupies the 16 KB block to this particular 3 KB process, and this 13 KB is internally fragmented to this particular process. We cannot use it, right? Suppose after that, new process arrives. New process arrives P5. P5, it is of suppose size 15K. So again, it starts searching the entire list of the free holes. So free holes are only the two, this one 10 KB and this one 4 KB. Okay, so 10 KB and 4 KB, both are not large enough because the process size is 15K. So there is no place to load the 15 P5 of the 15K. Actually, we have the memory available. We have the memory available here 10 KB, 13 KB, 4 KB, but 13 KB is internally fragmented, which we cannot use. And even if we have the memory available, this is in the non-contiguous fashion. And these algorithms, what we are discussing, these all are comes under the category of the contiguous memory fashion. So we require the contiguous block of memory. It is not available here. So that's why there is no place to load the P5. Even the memory is available, we are not able to load the particular process because it is fragmented into the parts. It is not in a contiguous fashion. So what we can do? So compaction is a technique to or tool or technique we can say through which we can avoid this. Let's see. So compaction is a method to overcome the external fragmentation problem. All free blocks are brought together as one large block of free space. Compaction requires dynamic relocation. Certainly, the compaction has a cost and selection of an optimal compaction strategy, which is difficult. So one method for compaction is swapping out those processes that are to be moved within the memory and swapping them into different memory location. Let's see how it works. So suppose this is the initial memory mapping, same mapping we are continuing throughout the explanation. So here it is the before compaction, this is the memory mapping. Now after compaction, what we are doing, we are swapping out the process P2 here. Okay, and after swap out, we'll swap in the process P2 next to the block which is available after P1. So you can see it here, right? We have swapped in the process P2. Now what we'll do, we'll swap out the process P4, okay, and then swap in next to the P2. Then we'll swap out the process P3 and swap in next to the P4. So now you can see that this much block is contiguous block of memory which is available, right? So memory mapping after compaction. So free memory is of 27 KB is available. Now the P5 of 15 KB can be loaded here. So we can load the P5 of 15 KB and then still we have the free block of the 12 KB. So this is how the compaction works. The fragmentation, which we have used the word over here, there can be of two types of fragmentation: external fragmentation and internal fragmentation. So you can see this is the memory mapping. So suppose there are in contiguous memory allocation, there are two types of the memory schemes, that is a fixed partitioning method and the variable partitioning method or dynamic partitioning method. So in fixed partitioning method, suppose the partitions are of the fixed size 2K, 6K and 12K. So this 6K, this is empty. Suppose we have the process size more than that, we cannot then in that case will not occupy that because it is fragmented. So if a whole partition is currently not being used, then it is called as external fragmentation. And if internal fragmentation, for example the block size of 12K, out of the 12K we are using only the 9K, so 3K is internally fragmented here. So if a partition is being used by a process required some memory smaller than the partition size, then it is called as internal fragmentation. One more definition of the external and internal fragmentation we can see here, and then we'll stop here. So external fragmentation, total memory space exists to satisfy a request, but it is not contiguous.
Total memory space is available in the memory, but it is fragmented in the part. So we cannot allocate it, but because it is not contiguous, so that is external fragmentation. And internal fragmentation is allocated memory may be slightly larger than the requested memory. And this size difference is memory larger than the requested memory. This size difference is memory internal to the partition, but can not being used and not being used by this process which to which it is allocated, and as well as we cannot use it for some other processes because it is internal to the partition. So first fit analysis reveals that given the n blocks allocated, so zero point 0.5 n blocks lost to fragmentation. So the rule may be, you can say that one third of it may be unusable. So that is the 50% rule. So one more topic, relocation. So as compaction we have seen, so static relocation and dynamic relocation. So static relocation means what? A process may be loaded into the memory, each time possibly having a different starting address, which is necessary for variable partitioning. Whereas in dynamic relocation, in addition to static relocation, the starting address of the process may change while it is already loaded in memory, which is necessary for compaction. So for compaction, dynamic relocation is must.